Hey guys, welcome to another episode of AI for Lunch. This is episode 13, and I'm calling this episode Getting Intuitive About Gen AI. As a background, I've been talking about AI in this channel for going on 6 months. And as I mentioned before, I've noticed that the mood and the attitude regarding AI has actually changed, probably for the better. When I started this channel, the mood was very decidedly negative. It was all about gloom and doom. It was all about existential risks. That's certainly still an issue, and I will probably devote another episode to discussing kind of the nuances of AI safety as well. But for now, I want to focus on in line with the change in mood. People have become more practical about AI. They're looking for ways to put it into practice in business and their day-to-day lives, which I think is quite a positive development. But at the same time, I still in the number of people I meet. I also have been conducting talks and events. It seems like for the most part, AI is still this mysterious technology that people still struggle to grasp, even though we have been talking about kind of the practical implications about AI, kind of the layman understanding of how it can help us, areas like creativity, productivity, knowledge management. I still think that people generally lack kind of a deeper understanding of how AI actually works, with the exception of those who actually build these systems, who get into the technicalities of it, the programming part, the mathematics of it. Certainly, they would understand how AI works. But I think there's probably still a middle ground to be sought, where users, non-technical, non-builders of AI can still grasp on an intuitive level how these models work. And I think we might as well get the ball started on that by talking about going maybe one level deeper from kind of the broad view of how AI affects us and the world, and start opening the hood, so to speak, and seeing how these, what's inside some of these models. How did they come about? How did they develop? And that's going to be the topic for today's episode. So, for those of you who don't know me, my name is Doc Ligot. I spent the better part of my career in financial services, and then moved into technology. And now I'm a data entrepreneur, so I run several AI companies. My current focus now is on capacity building. So I have a broad vision to educate as many people as possible, 1 million Filipinos in AI. And I also want to contribute to jumpstarting the AI startup sector in the Philippines, which I feel is still non-existent. At the same time, I also want to draw on my background. So I spent, as I said, many years in financial services. That's why I learned most of the skills, my skills in data science and analytics. Then moved into IT, and then for several years, I also spent some time over the pandemic working in the humanitarian sector. So using data, artificial intelligence, remote sensing to solve problems like public health, food security, human rights. Some of that work has been documented in previous episodes of AI for Lunch. So as a background, I'm actually quite, well-rounded. And I've been both as a user and a builder, as a consultant, a vendor, and also a client on the client side of data and AI. So I think that's where I'm drawing all of my, I guess, my insights that I'm happily sharing to everyone here. And then as a background to this, if this is the first time you're seeing this AI for Lunch, it's I started doing this 6 months ago as really a way of spreading broad awareness on AI. The target audience is both technical and non-technical. I think majority of the people watching this actually are non-technical, and they're liking the non-technical approach by which we discuss these things. It's not meant to trivialize the technicality of AI. It's certainly a fascinating, powerful, and complicated technology. But I think there's a lot more work to be done in bringing not just knowledge but access to AI to a broad audience. One of my early goals was to address alarmist claims, and I think for the most part, I think we've done a good job there. Disinformation about AI as well. we'll hope to dispel some more myths about AI today in this episode. But this still remains kind of an 18,000 feet view, maybe a little closer, like a 9,000 feet view. It's still high level, but a little closer to how the action works, because I really want to get into some of the innards of artificial intelligence in order to impart what I said, that intuitive view of AI, which can help you as a business user, as an executive, as a startup founder, come up with all sorts of AI solutions. That's really the main goal for this series. So I actually was, as of this recording, a speaker in several events just recently. No? One of the events was the Philippine Blockchain Week. And right before that event, I asked around my social media network, what's your take on what is the true nature of AI? And this is some of the stuff that I've seen. I would say a common trope is AI and statistics. This is also AI, statistics in data science, statistics in machine learning. So statisticians have certainly a lot of things to say about it. I think the underlying mechanism for all of this is really statistics. It's really math. And no one is denying that. But I think one thing that we need to start getting getting over with is it's not just about statistics. Certainly you need that for these tools to work. But I also sense that we can oftentimes fall into some sort of gatekeeping by saying, oh, it's just stat, or underneath it's all stat. Yes, underneath it's mostly stat, it's mostly computer science. But to confine it to stat and computer science would be, for me, the bigger mistake. It's got AI has massive applications everywhere else. And more importantly, it takes more than just statistical and computer science skills to make it work. I think that's really the brutal truth. Yes, you need people who know stat. Yes, you need programmers to build these tools. But as far as the usage is concerned, you're not going to get far if everything you know is just statistics. That's just me. It's a double-edged sword. Yes, it's both a blessing and a curse. I think I've talked a lot about the utopia and dystopia of AI. And this is something we also have to be comfortable with. With any disruptive technology, there's always a good and a bad use for it. And again, we don't want to fall into the doomer camp of just looking at the negativities, nor do we want to fall into the hyper camp, which is kind of like where everyone in the blockchain sector is. They still are hyping it as much as possible, even if the evidence is already presenting to the contrary. It's a different topic altogether. Let's not make that mistake with AI. And finally, this is Aid from my Twitter network. AI is nothing more than layers and groups of multiplied tensors passed through activation functions as you go from one layer or group to another. So how can that really have a nature? So it's actually a lot to unpack. That tweet actually speaks to this episode in the sense that, yes, there is kind of something mundane about how AI is in terms of it's simply just calculations done in a very fancy way. But to deny that it does some level of reasoning, to deny that it has some level of agency, to deny that it has actually an impact on humanity, again, would be the bigger mistake. So even if it is a relatively, I would say, mundane thing, it is not trivial. And yeah, hopefully we address some of that in this episode. So I'm going to jump into the rabbit hole by knocking off, well, not necessarily knocking off, but talking around a few of these commonly held or commonly heard statements about AI. It's been around. It's just an overfitted regression. I don't know if you've heard that. It's a black box. I think we've heard that also. These are just stochastic parrots. This sounds like a statistician talking. In other words, all they do is repeat probabilistic patterns. Certainly that's true, but is there more to it than that? This I heard very recently in another event. Some prominent data scientists said ethics is not something that STEM people or data scientists should mind or really mind about or are trained to mind about because it's not something taught to them in school. Actually, there's nothing false about that statement. I was part of a labor market intelligence study about analytics a few years ago on behalf of AAP for PBED. And we did look at a number of curricula for data science and analytics. And with the exception of a few, most curricula actually don't look at the ethical side, which I find interesting, disturbing maybe. But that doesn't necessarily mean STEM people should be blind to ethics. In fact, as I'll show later, a lot of the ethical issues actually have a mathematical component, and that's certainly something STEM people should be strong at. And then the last bit about average information. I've heard this thrown around recently that, these large language models, they don't do anything special. They just provide the average of the information that they get. It's kind of like how a regression coefficient is the average of, the possible variance around a certain variable. Again, there's nothing false about that, but whether the impact to us as a society or to individuals is also average, I think it's counterintuitive, and when I get to that point, hopefully you'll agree with what I'm saying. Okay, AI has been around for some time now. So I think there's a commonly held belief that machine learning is artificial intelligence, or deep learning is artificial intelligence. And I remember in the AI summit a couple of months ago, some people were surprised to hear that machine learning is not the totality of AI. There used to be, I think there still is, a field of artificial intelligence known as symbolic AI. So what's symbolic AI? Symbolic AI is actually a precursor to machine learning. It was the first attempt to try to reconcile a theory around, creating artificial intelligence. It's an older practice. It revolves around rules and symbols, basically. Machine learning is more about data and algorithms. Symbolic AI is about representing everything that we know in terms of rules and symbols. And I think for the longest time, this was, if I'm not mistaken, starting in the 50s, going all the way up to maybe the 80s. There was a search for kind of the rule book that will define AI. If you can reduce the totality of experience, the universe, into a set of rules, and you compile enough of it, that would be AI. While the machine learning school of thought is a bit more recent, started out probably in maybe the early 70s onwards, and a lot of the pioneers of machine learning are still around, like Jeff Hinton and his group. The thought process was, through data, you can teach AI, you can make it learn, and through algorithms, it maps out a representation of the data, and that represents the learning. So one is writing the rule book, symbolic AI, and machine learning is more about giving the AI the ability to learn its own way, learn its own rules. So, at the hip, it's also about representations and rules, but it's really more how that is done, So some of the people in symbolic AI, I think Jim Miraflor knows more about this. I had a conversation with him about this a few weeks back. Some names you can look up: Marvin Minsky, John McCarthy, Alan Newell. They were the ones who pioneered and pushed the practice of symbolic AI. So what is the kind of the main ideas behind symbolic AI? Number one, knowledge is it's about storing knowledge in a structured logical format, like a library. So it's not much different from like a database, So you want to codify things that represent knowledge, like rules and symbols. And then you have to define these rules to allow the AI to deduce conclusions. So if-then statements, if the pot is smoking, it's probably hot, something like that. And symbolic AI also looked at representing things as symbols and then manipulating these symbols into logical sequences that allow the AI to make decisions. So that was the kind of the thinking behind symbolic AI. Now, it's no longer I wouldn't say extinct, but it's no longer a popular field of practice compared to machine learning. Several reasons why. Number one, it's really hard to scale. You know, just how many rules can you write down before the whole thing just becomes too ungainly? So hard to do. It's very arbitrary. It's also inflexible at a certain level because you can write a set of rules, for example, to capture one view of reality. But then when you approach it from a totally different view, some of these rules fail. In fact, some of the basic tenets of physics represent that failure. So if you can't, if, for example, you can't reconcile Newtonian physics with relativity, what more, at the computer science level? And then I think the practical problem with symbolic AI is how do you keep the brain up to date with manual effort? Every time you discover something new, you have to add a rule. Remember, symbolic AI is not machine learning. In other words, it has to be a deliberate effort to compile. So there was no agreed system across all of the practitioners on how to update that knowledge and information. Unlike machine learning, you had a process like backpropagation that allowed weights and biases, which we'll talk about later, allow the machine to learn with new information. Those weights and biases can be recalibrated. So in many ways, machine learning was not just an alternative. It was a reaction to the limitations of symbolic AI. And then finally, symbolic AI, in my view, didn't know what to do with data because they were more focused on rules. While machine learning, it was sort of, in hindsight, a bit more straightforward because the rules of machine learning were derived from data. Symbolic AI focused too much on creating rules, creating frameworks, creating symbols. While machine learning said, you know what? Forget about any of these preconceived notions. Just give me a data set and an algorithm. The algorithm became the framework. And then the backpropagation process was the one that kind of found all of these, all of these rules after the fact. So at the end of the day, machine learning, although I wouldn't say it's the perfect solution, but right now it's the workable solution, came from the symbolic AI as a reaction to the symbolic AI movement. And in a way, proved more effective, at least for now, in approximating knowledge, gathering new knowledge, and updating knowledge. And then now with these automated tools, we're, I think, much closer to approximating true intelligence. And whether we've reached that pinnacle or not is another, story altogether. But, hopefully you get my drift. So in a nutshell, the answer to the question, yes, AI has been around for some time now, but not the AI we're familiar with. It was symbolic AI that was the rage for years, decades. And then later, as computer processing. Oh, yeah, another thing to point out. So the machine learning school of thought wasn't very popular when it came out because the capacity of hardware and software, basically computing systems, to perform data analysis and algorithms was very limited. And you need powerful data processing to make machine learning work. Now, obviously, that started to change when computers became more powerful. And especially now with the advent of GPUs, which can perform parallelized computations, we're now closer to the ideal environment that now allows machine learning and deep learning to be maximized. So in a way, what really brought AI to its current stage is not just the theoretical kind of algorithms themselves and not just the theoretical mathematics. It's really the hardware, Now that we have better hardware, we can achieve this. So let's talk about that school of thought, the machine learning. And again, this is going to read like some sort of a data science textbook. But to develop an intuitive understanding, let's also focus on, when we talk machine learning, there isn't one type of machine learning. There are many. And these three are probably the most contagious groupings, no? And in a nutshell, when you say supervised learning, you're giving a known pattern to an algorithm. Like if you want to detect cats, you give an algorithm images of cats that have been tagged as a cat. and then images of things that are not cats tagged as not cats. And the difference between these two groups of data will be what the algorithm decides eventually to use to discriminate future pictures. That's why it's called supervised. You're giving ideas already, preconceived, pre-labeled ideas. It also applies to more, I would say, more fundamental processes we do in statistics, like forecasting, regression. These are all forms of supervised learning where you gave historical data to an algorithm. The algorithm learns that pattern, and then with new input, is able to extrapolate and project that pattern in the future. So supervised learning is usually the most precise type of machine learning because you already know what you're looking for. It's just a matter of generalizing across data points so that you know future examples when you see it. Now, unsupervised learning is kind of the conceptual opposite. You can start with data that you're not familiar with. You don't know what the labels are. You just want an algorithm to look at patterns. And this is actually the school where generative AI emerged from. So I'll get into that in a bit. So this diagram here is a clustering analysis where you have groups of data. You may not know the underlying structure. Maybe there is, maybe there's not. But just through the raw behavior of the data, an algorithm will be fine looking for patterns. Now, unsupervised learning can become supervised later on if you agree that, okay, certain behaviors, certain patterns, this becomes a label. Like maybe I say one of these clusters represents something I'm looking for. Maybe this represents the ideal customer, or this represents fraudulent transactions. You can now use that distribution in a supervised manner. Can you look for more examples of data that resembles that? So you can see how supervised and unsupervised learning work together. In fact, that's how generative AI later on will be created. Reinforcement learning is something less common, but it's also been around for some time. Now, the idea here is you are training an agent to interact with an environment. So that's how a reinforcement learning problem is set up. You have an environment, and the environment has some rules, and then you have an agent who may not understand those rules, and they'll have to learn those rules from scratch in order to pursue a goal. So this is best visualized through a game like chess or Go. There's the rules that govern chess. Each piece can only move in a certain way. And you train the machine learning agent to work within those rules with the goal of defeating the opposite side. And then through repetition, it'll try many, many, many random combinations of moves that satisfy the rules until it finds a pathway to the objective. Now, this type of learning is actually what's birthing a lot of the Hollywood view about AI because, in a way, it's closest to an intuitive understanding of how things can learn. You learn by repetition, you learn from your mistakes. Although that process actually exists in all of these tools. When I say backpropagation, that's really the learning through your mistakes. So backpropagation is essentially the process where you alter weights and biases within a given algorithm or framework that reduces an error towards a goal or maximizes the likelihood towards the goal. So again, going back to the symbolic versus machine learning debate or school of thought, this is how the machine learning school of thought cracked the problem. You don't know what the rules are. You specify a framework by which the machine will attempt to figure out the right answer. And then you give it a process called backpropagation to repeatedly try many, many answers until finally it gets to the outcome. So these are the three types of machine learning. So these three types of machine learning support the two types of AI that we've been discussing from episode 0, the discriminative AI and the generative AI. And again, discriminative AI is meant for insight and interpretation. So you give it data and it tells you something about the data. I'll give it a cat, it tells me that's a cat. Or I'll give it a picture of a person, that's not a cat. Because the algorithm had already been trained through backpropagation, through supervised learning, to identify what cats look like. While generative AI works differently. It has learned patterns that describe certain phenomena through different types of processes. I'll get into it in a minute, with the intention of producing more variations or more versions of that data point. So I'll give it a cat, it'll give me more cats. I'll prompt it with a word like cat, which has been embedded into the data representation of images, and therefore it produces cats. And as I keep saying, this maps very well to traditional views of the human brain. Discriminative AI is perceiving, its logic, its insight, while generative AI is more expressive, creative, and this is where a lot of the current excitement around AI is currently. So things like deepfakes, so random samples and variations of a theme, these are all men, women, and children of various racial, tones. How does it know to generate these racial tones? Well, obviously it learned from past examples. Or these are images from Midjourney following a prompt. How does Midjourney know that man turning into an eldritch god should look like this? Presumably, it has learned that relationship between the text and the images from past, data. Or the chatbots like ChatGPT. How does it know to answer a certain series of words after a question? It certainly learned that from past data. Like every time this word appears, most likely this next word appears. So I'll talk a little bit about that. That frame of thought or that kind of thinking didn't just appear out of the blue. So in order to understand this better, it's good to look at the evolution of what we now call generative AI. And as you'll see, the intuition wasn't very clear from the very beginning. The thinking that got us to where we are now started in a very different way. Okay, so let's start with what I would say is one of the earlier pathways getting to generative AI, the autoencoder. So an autoencoder, in a nutshell, is a process that gets a data point, say a picture of a cat, compresses it into a representation, and then decompresses it back to a reconstruction of the original data point. So the first thing you should know here is that there's not just one, but two models working in unison. There's the encoder and the decoder. And the encoder's role is to compress this information into a small space. And the decoder's role is to decompress that small data set into the original data point. And the encoder, decoder, or autoencoder, these two models know that they've done their job if the difference between the first data point and the reconstruction is as small as possible. So you look to minimize the error. And the moment you get to that point, maybe you've reconstructed it like 99, it's never going to be 100%, like 99.999. So think of it like information loss. If the information loss between the first image and the second image is as small as possible, then you've already reached a convergence. So why is this significant? Well, autoencoders were designed for compression purposes, kind of like a zip file, if you're able to compress large data into small data and then decompress it back with very minimal loss of information, that is a useful tool. It's useful for telecommunications, network signal processing, data storage, etc. It's also useful for encryption. So you get a data point and then put it into a form that's hard to interpret because it no longer resembles the original data point. But you have a decoder key that can restore it back to its original shape. That's also powerful from a security standpoint. This is, I would say, the granddaddy of the kind of the pack. There could be earlier models, by the way, but in terms of intuition, this intuitively felt like the start of it. So if you now have a process that can compress and decompress data with minimal loss, this compressed information takes on a very, very crucial role. Because in a way, this represents the knowledge that you have in a very small compressed space. That is the essence of this autoencoder. And these two models work in unison to lock and unlock that information. So how does it become generative? Well, by straightforward, it is a generative algorithm because it's able to generate basically a twin of the original data point from from this compressed space. And this is where the next step becomes important. So if you can do an autoencoder, then a variational autoencoder is, a logical step. How does that work? Again, you have an encoder, and what it does is it compresses a lot of information into a small space. We now have this representation that represents, let's say, many cats. And then again, through the same process, you are able to train a decoder that can then restore these cats to their original shape, but with a twist. Since you now have a compressed space that represents all of the information that you had, namely all of the cats, you can now work it out so that you can query this space similar to how you would query a database, but not exactly, because you're not retrieving records per se. What you're doing is reconstructing records in a synthetic way. You're creating synthetic data based on an input into this space. So this is the early, I would say the early emergence of prompting, So, but you don't prompt with any word. This is just a number because you're able to compress all of this information into this small set of numbers. So let's say there are, 256 variations of cats compressed into this space. And you can now just query, okay, give me variation 10, variation 11, or the cross between variation 9 and 10, something like that. And because the decoder understands how this structure works, it's able to reconstruct a synthetic version of the original. And this is going to lead into the deepfakes soon enough. In fact, the earlier deepfakes were via variational autoencoders. So you can see the jump from the original autoencoder, which was focused mainly on the compression or the encryption of the data. You can now use that encrypted or compressed space as a representation that you can query, and then now you can generate new images. Now let's talk about GANs, Generative Adversarial Networks. So this works similar to the variational autoencoder, but instead of manually querying or prompting the representation, this works in a slightly different way. You also have two models, a generator and a discriminator. The generator creates synthetic data upfront, but it doesn't know what it's creating it for. So it's pretty dumb. It comes up with random types of info. So it might not even know it's creating cats. It's just creating information. While the discriminator has been trained with existing cats, existing data. So it understands what a cat should look like. And the whole process of a GAN works such that the generator keeps feeding synthetic data into the discriminator. And the discriminator rejects it if it doesn't like what it looks like. So it doesn't look like a cat. Nope, 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 nope. Until such time the generator gets it right. So this is now the kind of the machine learning, the backpropagation approach, where we're testing how well the generator is able to mimic what a real cat looks like. And the moment it passes the discriminator's taste, basically it's been able to fool the discriminator, then you now have synthetic data. So this is way better than a variational autoencoder in terms of accuracy, because although the variational autoencoder structurally makes sense, its ability to produce data that's completely synthetic but looks authentic wasn't very good by the structure. But a GAN could provide very, very lifelike or very authentic looking images that resemble past images, but it's completely synthetic. So this is how style GANs were created. This is how deepfakes were created. And up to this day, GANs are also being used for other purposes. This is also where whenever I keep talking about differential privacy, I actually refer to the GAN and the variational autoencoder. So think about the current challenge now with privacy, where if you have data, generally from a privacy standpoint, that data may not be used. Let's say it's medical records, you got to lock down that data. You cannot be leaking patients' information that's supposed to be private. Now, with a GAN or a variational autoencoder, what you can instead do is get the data set that represents real patients and use these algorithms to generate synthetic patients through a GAN process or a variational autoencoder process. And what you will eventually end up with is a data set of patients that don't map to any specific individual, because these are all fake patients, but they have the same characteristics as a whole as the original data set, which you can now analyze. So there's a lot of work that's being done now about analyzing synthetic data in lieu of actual data and checking if the insights from the synthetic data map to the original data and can then be used for other purposes without compromising the privacy of patients. That's what I mean. And a lot of people who reacted to my post about synthetic data kind of missed the point. A lot of them still think I'm arguing I'm arguing in favor of interpolation or SMOTE or averaging out blanks in a data set. No, of course not. Those are very, very basic versions of a GAN or variational autoencoder. And there could be, through the new generative AI processes, better ways of coming up with these synthetic data sets. So I think in the near future, synthetic data will be a major part of day-to-day life, Which brings us to where we are today. So the transformer is the current algorithm powering large language models. And then I'll shortly talk about diffusion models, which power the image generation tools. Now, to talk about the transformer in really, really fine detail will take a long time. So I'm just going to give you the high-level version. So a transformer is also an encoder-decoder architecture. As you noticed, all of these models are there. There's always two models. What the encoder does is it gets sequences of text and then embedded with positional encoding. So when you say positional, it memorizes the relative positions of words, like hi is number one, how is number two, etc. Through a fancy way of encoding that position. And then in a very, very elegant way, creates a representation of all of that text in relation to each other. And that representation is called attention. In a very high level, attention is a matrix that relates the relevance of a word with another word. So you have this massive matrix of every possible word that you've encoded, and each word will have a relative relationship to every other word. And this is the secret that allows a transformer to start guessing what the next word will be given a series of past words. So that's encoded into this input representation. And then a decoder will do the opposite. The decoder, knowing this input representation, will take a sequence of words and then through an attention mechanism as well, decode that and give you an answer. Now, the answer depends on the kind of the relationship that was trained. So the earlier transformers were actually trained for machine translation. In other words, translate an English sentence into French or Tagalog to English. So the attention mechanism would be relating English words with Tagalog words in that case. While the large language models were trained to replicate what the next word would be given a past series of words. So the attention would be what would be the relationship of a word be relative to the past words that came in that sequence. And as I keep saying, by training this process, we've inadvertently provided models with knowledge of language. And language is a great representation. It's not complete, but it is a good approximation of human existence, of human society. Because a big chunk of society is actually encoded into text. And this is actually the secret sauce why large language models were surprisingly useful, because scientists actually weren't that excited about it. These things have been in development for longer than we know ChatGPT has existed. But who knew that a model that could do question and answer relatively accurately would be groundbreaking? Diffusion works in a similar way but different. So similar to the previous models, this is also an encoder-decoder process. So you have an image, and then it's given an image, it's encoded with noise. So you create a fuzzy version of that image as a first step. Then as a second step, you take that noisy image and then denoise it, but then add additional information into that denoising process. In this case, an embedding of text. So you have an image of a noisy image of an orange cat. You're going to embed that with the word orange cat. This is a very high level, explanation of it. And then denoise that back into the original cat. So if you're able to do that, you now have this representation. Remember, this is the key to all of these models that can now relate a text, phrase, or embedding with a picture. So now you can keep querying this, similar to variational autoencoder, querying this with the prompt, like an orange cat, and it will generate an orange cat. And think of how many images were indexed by the likes of Stable Diffusion, Midjourney. There's going to be a Dolly 3 soon enough with that process. And you can now generate these really fantastic, synthetic, accurate images through this diffusion process. So I think in a nutshell, before we move on to kind of other things, this generative AI was brought about by a slight change in approach. Rather than just having one model interpret data into something, you have a second model that decompresses or decodes that something into another data point. And it's really that process that makes the generation possible. So when I say that generative AI creates data and discriminative AI interprets data, I'm actually missing a half step. Because generative AI, for it to generate data, it must have also understood and interpreted that data to begin with. So it's kind of like a two-step process, where the original discriminative data just stops at the interpretation or the insight. Something to think about from an intuitive process. Okay, that's step one. Okay. What about this thing called an overfitted regression? What's the big deal with overfitting anyway? So those of you who are doing data analysis would be familiar with the concept of fitting. Fitting is basically learning. So if you have data points, the line here is a representation of the pattern learned by the machine learning model. So it just says here, as more time passes, values go up. But do they? So as you can see, obviously there is a period of time where the values were going down, and then later they were going up. So the better fit would be this thing in the middle, where it's actually more of a curved line that captures the real trend of the data generally, but you still have errors. So the line isn't exactly capturing all of the points, but generally the behavior. And then an overfit is you have a line that intersects with all of the points. In other words, it's come up with so many variations and patterns from the same data. It does capture the data per se, but one thing that is counterintuitive here is, even though the accuracy of the line in the overfitted example is higher because it's able to hit most of the points as opposed to this, it's generally useless as a predictive tool, because if you use this trend, the next point in time would be predicted to go down because of this new trend, while the perfect fit or the good robust fit would generally predict it to go up. And if the same tendency persists, then it'll probably be correct. Another way to appreciate this is from an error perspective. So underfitting and overfitting. So during an underfit, during a machine learning process, generally, an epoch is how many times you've run the training algorithm, the backpropagation. The more time you spend training an algorithm, over time, the error of the training goes down up to a certain point. However, the value of the prediction depends on the fit. During an underfit, the value of the prediction, the error of the prediction can be quite high. And the more you train it, that error tends to drop. Now, at the robust fit part, this is where both the train and the test errors are at their lowest. In other words, the prediction and the original training capture the behavior of the data. Now, at an overfit, although the training continues to learn more, because you can see the curve line becomes super squiggly now, and it's now mapping each and every point, but it becomes less predictive as a result. So the test error starts climbing. So you can see that kind of the relationship. At the underfit, both the test and the train error are high. At the robust fit, both the train and the test error are low. And then on an overfit, the train error is low and the test error is higher, interestingly. So that's why you don't want to train the machine learning too long because otherwise it starts mimicking the past and doesn't do well in the future. So this is a visualization of exactly what's happening, when we train a machine learning model. So this is a linear regression. These are your input variables. Let's say you have 4 variables in your data set. And what a regression does is iterate through weights. So the weights are multiplied to the value of each of the input. And then there's a bias or the intercept. This is like a balancing figure. And what you're training here is to minimize the error between the actual data and the predicted data. So the activation function is that error correcting mechanism or error rate. If you're able to minimize that error given a certain combination of weights and bias, then technically you've found it. Now, what's sometimes counterintuitive is this is exactly what's happening in an AI algorithm or a neural network, except you only have one node. So whenever you see many, many nodes in a neural network, each node does this particular process. It tries to minimize an error to an outcome. So you can argue that a regression itself is actually a neural network with just a single node. Now, all neural networks actually have many, many nodes. So you can have the 4 variables, and they're fed to many of these nodes. So you can imagine each of these nodes as an individual regression calculation. And the outcome of all of these nodes would be a classification like dog or cat or, predictive value. So why do it this way? Well, many reasons. Number one, complexity. So a linear regression works perfectly if the data has a linear relationship. No? For example, as more time passes, the values go up. So really the trend is a single line, and you can achieve that with a single node. But there will be cases where the relationship is a nonlinear. There can be many combinations. Like, for example, how do you recognize a handwritten digit? There's no linear relationship between the presence of a pixel and the value. So that's why you have these architectures. What they're able to do is capture through statistics, but not in a linear way, all of these relationships. And the deeper you are, that's what leads to deep learning. So deep learning is nothing more than very, very deep and complicated neural networks that are able to capture many relationships. So when we talk about the transformer networks and the diffusion networks, for instance, they're able to map very, very complex relationships between one word to each word in multiple ways, such that it is able to generate language. It is able to generate conversation. So a neural network is essentially many regressions. So the answer to the question, a neural network is just an overfitted regression. It's more no than yes. Yes, there is some regression being done and fitted, but there's many of them being done. So academically speaking, you could have an overfitted regression here, but the other regressions kind of offset it. I'm sure you can prove that mathematically in the classroom. But the idea here is these neural networks are actually quite robust, and they resist overfitting, primarily because of their nonlinear relationship. They're able to capture many types of relationships. So in theory, it wouldn't be an overfitted regression. So a regression is only one node. Okay, black box. So actually, this leads quite naturally to this point. We're used to, for the most part, dealing with statistical models. They're really quite simple, like a linear regression. You kind of know the weight for each variable. So you know that, okay, every time a person is a male, they have a higher chance of, getting a gun or something like that. So you know that variable with this weight has that relationship. While a neural network has many, many possible relationships for the same variables. So by virtue of that, people say it's a black box. Now, I used to think of it that way as well. But if you look under the hood and see how a neural network actually operates, it's actually quite transparent, So this is a visualization of how the number 2 is learned by a neural network to be a 2. So this squiggle, all of these pixels, 784 of them correspond to an input node, and they're run through these 2 layers of nodes. So you can imagine each one of these is a regression happening with inputs from each of the pixels. The pixels is a value from 0 to 255, depending on how intense the color is. And through this complicated network, it's able to infer that this squiggly line. So imagine of this as each pixel is a column in a data set. It's now able to learn that, hey, look, this is probably a 2. How does it do that? It's quite transparent. How is it interpretable? That's the problem. Each of these nodes handles a specific component of identifying this as a number 2. And that's not predetermined upfront. It's actually something quite, it's the feature of neural networks that itself discovers the features that identify the outcome, as opposed to a traditional statistical model where you specify the features upfront. I know there's one feature for every variable. Here, there may be 784 variables, but the features of each variable, is quite hard to track. It's really the neural network later on that determines. So in a way, it's kind of unsupervised in that manner, but the outcome is, a classifier. Here's another look at it, the number 9. And this visualization shows you that at each level of the neural network, how much of the figure 9 is being learned up until the last point where it pretty much just identifies that every time you have a circle and a tail, it's probably a 9, as opposed to these other numbers. So think of it like it's somewhat akin, inspired by the human brain, actually. But we're not saying the human brain functions like this, but we're just saying that each component of a neural network corresponds to a feature that no one pre-identified. The neural network identifies it itself. And then after the fact, you can actually open up the neural network. I'll probably do this in another episode and see which of these nodes actually contributed to that prediction. So in many ways, it's actually a very transparent box. Now, the interpretation of that is the question. There's actually a field in AI safety called mechanistic interpretability, which attempts to find ways to generalize the tendency of certain nodes to light up given a particular input, in this case, a handwritten 9. But I hope you get what I'm saying, that neural networks, they are quite transparent. What makes them appear like a black box is there's no straightforward way to interpret how the nodes are lighting up, except that we do know how they light up, and we do know what combinations of nodes actually end up going to an outcome. But it's not kind of interpretable in the the standard statistical sense. If you can understand that. Okay, stochastic parrots. This is a little shorter. So to many people, when they see LLMs, it sounds like a glorified autocomplete. And in many ways it is. So given a certain word or combination of words, it starts inferring what would be the likely next word. That's pretty straightforward. The transformer, as I explained earlier, does that. Now, what's counterintuitive is it's not just because it just interprets the next word after a series of words, doesn't mean it's just limited to that. That's actually the base task that it was trained on. But as a result, it's able to come up with, I would say, a very, very impressive low-level reasoning ability. So I'll give you an example. I prompted ChatGPT with this. Here's a process. Get a cup, add some milk, add some sugar, add some coffee powder, add some ice, and then drink the coffee. What's missing in this process? So think about it for a minute. From a standard computer science perspective, how would you solve this process? Number one, you need an algorithm that understands what the process is. Number two, you need an algorithm that can identify gaps in a process. So it must have learned what a full process is in the past, and it's able to abstract it. Third, it must understand what coffee is all about and drinking coffee is all about, and what does sugar, ice, cup, milk mean. So think of it like symbolic AI. All of these are symbols, and you need rules for everything. So quite impractical from a symbolic AI standpoint or any other standpoint to train a process to figure this out. But out of the box, the large language model knows what I'm missing. So it says, in the process you provided, there are a couple of important steps: boiling water, brewing coffee, stirring, straining, and optional additions. So therefore, the revised process might look like this. Get a cup, boil the water first, then add coffee, brew the coffee, then add sugar, then milk, then stir, then strain, then add ice, and then add your flavor, and then you drink the coffee. So by this standpoint, if we're still stuck with the stochastic parrot analogy, I think we're missing a lot. It's not just about predicting the next word. That was the base task that it was trained on. But what we ended up with is a model that understands language. And if you have a model that understands language, you have a model that understands part of us, part of humanity as captured in language. Some people ask, so does that mean large language models are already AGI? That's always a philosophical question. And I don't know the answer. I don't think it is. And the reason for that is simple. When you interact with the world, do you think in terms of text? You probably don't. Like as you're listening to me now, although you're reading text on your screen, you're probably not thinking in terms of words. Words are just the outcome of our action. And these models are all about words, just words. So if you wanted to approximate AGI, in my view, intuitively, you need a model that can appreciate not just text, but all types of sensory input. And maybe you're closer to what general intelligence is. Because, in theory, that's how our brains work. Our brains don't just work on the basis of text. Text is probably the smallest part of what our brains does or do. Language is also a small part of what the brain does. The brain interprets many other things. So the path to AGI, if we're going to use the brain as the analog, might require other data points. On the other hand, there's no rule or reason why AGI needs to follow humans. In other words, or AGI needs to mimic human processes to be truly intelligent. That was a question I asked Jim Miraflor before. Is it enough to just mimic humans? Or does it really have to think like a human for it to be called intelligent? And again, that's a kind of a rhetorical question. But I hope you get what I'm saying about this, just going back to this point about stochastic parrots. Yes, that was the process it was trained to do. But what we ended up with is something more than that. Is something that can think at a very, very basic level, but highly accurate level. And, that power is at our fingertips now. Okay. Ethics is not STEM. I don't want to sound like a nitpicking on an issue, but I think we do ourselves, AI practitioners, data practitioners, a massive injustice if we readily admit upfront that we're not trained in ethics. I don't even think ethics is a matter of expertise. It's not something you should be an expert in. It's something you just practice. It's something you should imbibe. It's closer to values. It's closer to principles. It's closer to heuristics. So I think we might be hitting the nail on the wrong. We might be hitting, the nail in the wrong direction by arguing something that needs to be taught. Certainly, it needs to be discussed. It needs to be solved for, but it is not a matter for experts to decide on. It's really more of a societal thing. Now, what I want to clarify though is when we look at ethics, there's actually parts of AI ethics that are not just philosophical, because maybe that's the impression some people have that, it's all about philosophy, it's all about social science, all very fluffy. No, actually, no. A big chunk of the AI ethics problems are actually quite mathematical in nature. And here are this is not a comprehensive list, but here are some of the top three in my view. First is the concept of model drift. I talked about this in another talk where the data that you use to train a model may no longer represent the data outside because things change. The best example I can think of was the COVID pandemic, where you had society moving in a certain direction, and then during the lockdowns, they behave in a totally alien way. So if you had models and systems that were trained on that old behavior, they all failed under the new paradigm. You saw this happen when the oil market became negative because the world couldn't appreciate such a sudden lack of demand for petroleum. So markets were pricing oil at a negative value, which was unprecedented. Or all of the economic time series just couldn't work, I talked earlier about how neural networks solve for problems. This speaks to unknown distributions. We don't know upfront how the data, we know how the data looks like, but we don't know how upfront how the data will lead to a prediction. That's a totally unknown distribution until the neural network figures it out. And then lastly, this is a bit of a Hollywood example, but when we have automation, the specification of the automation needs to be calibrated properly. Otherwise, the agent will interpret it the wrong way and solve for it the wrong way. It might actually hit the outcome, but it never gets anything done. And that's what's happening in this game simulation where the boat was given a goal to maximize the high score and it never finished the race. It just kept picking up bonus items. It learned to do that by learning the rules of the environment, such similar to chess, no? So all of these issues are actually mathematical issues. Model drift can be calculated. The distributions of the nodes in a neural network are quite transparent and they can be learned after the fact. And reward misspecification can be measured. You can measure it by looking at activities of the agent and set thresholds and rules that, okay, if, let's say in this boat example, you can measure how long the agent is taking achieving the goal. If it ends up never finishing the race, then the amount the agent is taking can be quite long, if not infinite. And that can be gated from a mathematics standpoint. You can set a rule there. Okay, you should solve for this goal within a specified time period and finish the race. And if you add these two new rules, the agent will change its behavior accordingly. And it may now start solving for the goal aligned to what human beings want. So again, these are not intractable problems. They are solvable problems, but they are mathematical problems and you can solve it using STEM. You can solve it using math. I think it's more of the outlook. Like, do we really want to address these issues as STEM people, as data people? My answer will be yes. What's your answer? Okay, we're down to our last point about average. No? And yeah, certainly this is correct. I would argue that whatever the model produces is really the average of the sum totality of whatever it knows. But how it impacts us is counterintuitive. To explain this, I think we need to reassess what average means. Most people associate average with the Gaussian distribution, a normal distribution or a bell curve. And I think this is a misnomer. It applies to certain characteristics like human height, maybe your waistline. But when it comes to performance, it's been proven that humans actually align closer to a power distribution or the Pareto rule. So you have 80% of the outcome generated by 20% of the population. And 80% of the population are marginal contributors to the outcome. And that means the average is actually shifted left. Most people are actually below the average. So this is sort of a philosophical point. But if we argue that AI produces average results, that's actually much better than most people can produce. And by giving people access to the average, we actually improve the 80% somehow. Now, intuitively, this is already being observed in recent events. Like there's this article that I keep citing in my talks about a call center that experienced a 14% uplift in productivity using ChatGPT. And the interesting thing is that 14% is not equally distributed. The less skilled or less experienced workers achieved on average, higher performance improvements. A blended rate is 14%. But for the less skilled workers, they experienced more than that. And a more recent study by Boston Consulting showed that in the same way, ChatGPT also improved the performance of their consultants. Same thing. The less average performing or below average performing consultants benefited most from AI, while the above average performers had marginal gains. So if you're already good at your job, AI won't help much because it mimics what you do. But if you're part of the 80%, and the odds are you are, the odds are most of us are, then AI can only be better. It can only be an improvement on what we do. So that's a food for thought. Okay, so I think I'll end it here. I hope these discussions help not just clarify, but demystify the intuition behind AI. Certainly, we haven't completely discussed all of the aspects, but these are kind of the low-hanging issues that I keep encountering. And, again, the more we talk about it, the more we'll understand it. And hopefully, the more we understand it, the more we can adopt AI for our day-to-day tasks. Yeah. So anyway, with that, that's this episode 13 of AI for Lunch, getting intuitive about generative AI. Please continue to watch more from this channel. I have more content coming up, which will dive deeper into how AI works. At the same time, continue to discuss the practical implications of AI to society. So until then, I'll catch you on the next episode of AI for Lunch.